Oylum Hanım tamam diyene kadar ben bir şeyler anlatayım bu arada. Başlayabilir miyiz? Tamam. Ben 1994 yılında ODTÜ'den mezun oldum. Ondan sonra 2 sene asistanlık yaptım ODTÜ'de. 96 yılında Amerika'ya gittim. 20 senedir Amerika'dayım. Bu sene 20. sene. 20 senedir oradayım ama hayatım boyunca Türkçe teknik konuşma yapmadım. Yaparsam da yarı Türkçe, yarı İngilizce, yarım yamalak bir şey olacağı için İngilizce yapacağım konuşmamı. Çünkü bütün şu anda çalıştığım yerde konuşmamı öyle yapıyorum. Ama ondan önce bazı şeyleri size anlatayım. Burada konuşmamda öncelikle biraz şey yapacağım. Benim çalıştığım yeri anlatacağım. Çalıştığım laboratuvarı. Laboratuvar derken sadece benim grubum olan 25 kişi değil, 4000 kişiden bahsediyorum. Ondan bahsedeceğim. Ondan sonra arabaların tarihine gideceğiz biraz. Ne olmuş, ne bitmiş. Ondan sonra da şu an ne yapıyoruz, onunla konuşacağız. So I work at a national laboratory, and there's 17 of them in the US, 17 Department of Energy national laboratories. There are also Department of Defense national laboratories. They're not listed over here, but you can see them all around. Oops. You can see them all around here. Let me see if the pointer. And Oak Ridge is right here. Oak Ridge National Laboratory in Oak Ridge. There's Knoxville, Tennessee. You might have heard of Nashville. And here's Memphis. So if you look at the map over here, we're right here, southeast area. Some people might know Miami, Atlanta, Memphis. And when you look at our campus, actually it's not a small campus, it's like a university campus. Okay, here's a screenshot of the campus over there. Bunun pointer, biliyor musunuz pointer nerede? Arkasında. Tamam. Güzel. This is our campus over here. You can see everything started with this letter from Albert Einstein to President Roosevelt. He said, when he came from Germany, he said Germany is working on an atomic bomb. He said the US has to work on that so that we can compete with the Germans. That's how the Manhattan Project started, and that's how Oak Ridge National Laboratory was founded. When it was founded, the workers who built the lab, they didn't know what they were working on. Their families didn't know where they were. This was hidden in the woods, in the forest. So that's why it's called the secret city. I've seen some photos where they have overhead like carpets all around. They had fake trees and fake buildings so people wouldn't know what's underneath. Today, the nickname of the city of Oak Ridge is Secret City because of that. And now it's a national park. So this is Oak Ridge National Laboratory in 1943. The Clinton Pile, the building you see here, was the world's first continuously operated nuclear reactor. And today, if you visit us, you can visit this place. It's not working right now, of course, but it's a museum. So we have, as a lab, a $1.65 billion budget, 400 employees, 3,000 research guests, spent $500 million to get to this level. When I started at the lab, it didn't look like this, but it didn't look like this either. It was in between. All this area was a parking lot. So we have the nation's largest materials research portfolio, most powerful computers. 3-4 years ago, we had the fastest supercomputer in the world and the third fastest. Now, the one we have is second fastest. And next year will be fastest again. Next year, probably second, third. They check this every year. We compete with the Chinese and the Russians. So we have a neutron source for doing some materials imaging, better than X-ray. Research reactor. And we're also leading the ITER project for the US. ITER is a multinational project on fusion energy. And the US portion is led by the Oak Ridge National Laboratory. This is a nice campus, but my office is not there, and my lab is not there either. We're in a building called the Hardin Valley campus, not a building, but the campus area, Hardin Valley campus. It's right in between the University of Tennessee and Oak Ridge National Laboratory. It's straight right there. So this is I pressed the wrong button all the time. Okay. So this over here is the NTRC-1 with the Power Electronics and Electric Machine Research Center. This is the Fuels Engines Emission Research Center. This one is the manufacturing laboratory where there's 3D printing. I'm going to talk some about that. But most of the power electronics work is done here. There's also another group, Power Systems Group, doing this distributed generation work. Their lab is on the main campus. So let's talk about vehicles some. In 2011, when President Obama, by the way, his first name is not Barack or Barack. In the US, it's Burak. So it was really confusing for me in the beginning. Okay, I listen to the radio and they say Barack Obama and I'm confused. But anyway, in 2011, he said, we want to have 1 million electric vehicles on the road by 2015. Now we're in 2016, so let's see what happened. So this is a quote. I recognize a few faces here from me too. I gave the presentation at ODTÜ on Monday, so please don't give the answer. But so there's a quote I got from the paper. The electric automobile is in its heyday. Of the X many cars produced in the United States, 28% are powered by electricity, and electric autos represent about 1/3 of all cars found on the roads in New York City, Boston, and Chicago. What year? Any guesses? Come on, you can give me a guess. 2005? 2014? 1900. Oops, I'm going to quit doing that. Okay, so in 1900 there were 4,192 cars in New York City, Boston, and Chicago. Not everything started in the last few years. So if you look at the history of the electric vehicles, starting in the 1800s, starting in 1832, going all the way to 1900 when the electric automobile is in its heyday, electric taxis in 1897, Henry Ford introduces Model T. Here you see Model T over here. So if you look at the catalogs, you can find this page actually. There's a whole catalog, lowtechmagazine.com. You can see all the electric vehicles from that range. I actually have an electric lawnmower. I think it's as powerful as these, but I cannot ride it, unfortunately. I found this recently. So this was world's first hybrid built in 1896. Okay, it went up for auction for $175,000 or $275,000. I didn't really find out what the final value was. So the reason I'm showing you these things is we learn a lot from history. Electrified vehicles, electric vehicles didn't come out in the last 20 years. They were there before. Okay, so for example, I was reading somewhere. They said in the 1900s in New York, you could see in one corner 4 different technologies of cars. Steam-powered cars, electric-powered cars, horse-powered cars, and there's a 4th one, I don't remember right now, but there are 4 of them. Light rail, they said rail cars too. Actually, 5th one, they had the overhead-powered cars at the same time too. So what about hybrid, plug-in hybrid electric vehicles? 1900, the first plug-in hybrid electric vehicle by Ferdinand Porsche. You might recognize the name. It doesn't look like the current Porsches, but this one had wheel hub motors for the front wheels, all-wheel drive, and 4-wheel brakes. In '96, when I went to the US, when I visited GM, they were talking about in-hub motors, and I said, oh, that's a novel technology. In 2001, 2002, they started talking about plug-in hybrids. I said, wow, that's new technology. No, they were actually done in 1900s. So anytime we come up with a new idea, okay, anytime you come up with a new idea, you have to check if anyone else has done it. It happened to me a lot. Sometimes I come up with an idea, very excited about it, and then I find out 6 months ago someone published it. Okay, that's really important. So a newspaper quote from the same time, 1911. So electric vehicles are very handy for use in cities, and the numbers of best known and most prominent makers of gasoline cars in this country use electrics. So the same reasoning like before. The electric companies are anxious to connect their feed wires to these individual charging plants. In the US, it took a long time before the utilities were very comfortable in using the plug-in electric vehicles. Actually, I give this example usually. There's the biggest energy producer in the US, Tennessee Valley Authority. They were trying the retrofit plug-in electric vehicles, and one of their executives plugged one into his house. It burned down the front of his house. So after that, they said no more plug-in or electric vehicles at their houses. They're not going to be connecting that. This was maybe 2003-04 time frame. Today, of course, Everybody's interested in electric vehicles. Everybody's interested in plug-in hybrid electric vehicles. So let me ask you a question. Do you guys know the difference between hybrid electric vehicles, plug-in hybrids, and electric vehicles? Yep. Okay, good. One of the most popular electric cars right now is the 100-mile Nissan Leaf. Range anxiety is there. So here's another 100-mile electric car. 1908. I really like this title. The status quo of electric cars. We have better batteries, but same range. So 8 years later, we have electric cars that go for 100 miles. Great progress. And by the way, I really like high-tech stuff, gadgets and stuff. This magazine is low-tech magazine. There are some interesting things if you're interested in the history of technology. So what killed the electric car? There are two documentaries. One of them is Who Killed the Electric Car? The second one is The Revenge of the Electric Car. Okay, those are very interesting if you're interested in these. So in 1912, Charles Kettering invented the first electric starter. So if you remember, you've seen in movies, other places, you had to hand crank the cars, right, to start them. So that was a big problem. And actually recently I was reading more about this. Even they have some of those cars in the museums, and people trying to hand crank them, some break their arms so hard. So there were better and longer roads available for longer distance driving. People enjoyed that better. People wanted more power. We still want more power, right? Higher power cars. They're manly. People like that. Gasoline was a problem. They were able to refine gasoline better, so it was available more. And of course, the mass production of Model T. Going through 1966 to today. This time, the interest was more in either the oil embargo or the climate, reducing air pollution. Okay? Congress passes this, again, for zero-emission vehicle mandate. In 1996, when I first arrived there, GM EV1 was out. How many of you remember GM EV1? Okay, one. It was a very ugly-looking car, but it was very popular. And Who Killed Electric Car is talking about why it disappeared. They never sold it, they leased it to people, and then they took it away from them. People didn't like giving away their cars because they loved their cars, but they had to give them away. That car sold for $35,000, at least for $35,000, I guess. I don't think it was sold, but $35,000 would have been the value if it was to be sold. Now, if you look at the semiconductor history, 52 power diode, 57 thyristor, 70s MOSFETs, 80s IGBTs, 90s IGBTs widely available. This allowed for the Toyota to unveil Prius. Toyota vehicles, you weren't going to run them on MOSFETs. They wait for the IGBTs to come up. Later, you familiar with Tesla electric vehicles? Okay, they look nice, right? Well, original electric cars looked like this. They didn't look nice. So everybody thought the electric cars looked boxy like this. And there are photos I've seen. Tesla founder gave a presentation and showed some photos of electric cars, early electric cars, with engineers next to them with thick rim glasses posing with the cars. Okay, not very interesting to people. But then Tesla, they showed Tesla ads. Tesla ads had nice looking cars, sports cars, and they had models next to them. Okay, now people would want those cars instead of the cars with the engineers next to them, right? So that was the way they marketed the Tesla vehicle. So no power electronics, no problem. Early electric vehicles used DC motors. Okay, the speed was adjusted using a variable resistance, more or less. Of course, you had to change the brushes. Today we have AC machines, and you need to have the power electronics, of course, to convert and run the AC machines. And of course, as you all know, we can regenerate. When you brake, you can regenerate, and you can get 64% of the energy back, braking energy back, and charge your vehicle. Why 64? Why not 100? Because we all know there are losses, right, going back and forth. I think the number, this is for electric cars. For the hybrid cars, I think the number was around 30%. In addition to the losses, if your battery is fully charged, and if you're going downhill, if you're braking, that energy will be just wasted. It's not going to charge your battery if it's already charged, so it doesn't help you there. So who buys these cars? This is a survey from 2013. If you look here, most of the people who are buying these things are 35 or 45 years and older. And you see a lot of them, around 30%, making more than $200,000 a year. My guess is these people are interested in the Tesla more than the others, but you never know. And some people are buying this as a third car. I think they have two cars usually, and they buy it as a third car. The reason for this is the cars are still expensive. So did we make it $1 million? So this is the chart for up to September 2015. You see only 360,000 vehicles were sold by then. So we didn't meet the president's goal for 1 million cars. Of course, I don't think they sold like 700,000 of them after September in 3 months. But so the main reason for this is, as I mentioned, the cost is still there. A Tesla Model S costs around $8,000 right now. Nissan Leaf costs around $30,000 or so. But you can buy a similar car for $17,000 in the US. So why pay the extra money and then worry about the range all the time? So this is why the president came up with the EV Everywhere Grand Challenge. In this case, he wants us to have, he wants us to make electric vehicles more affordable and convenient to own and drive than today's gasoline-powered vehicles within the next 10 years. And this came out in 2012. So this is the 4th year we're in. So if you look at the targets, the part that's of interest to us is over here. Of course, the battery costs and the lightweighting, they're important, but the cost of the electric drive systems, we want to reduce them from $30 to $80 a kilowatt. So if you look at the Nissan Leaf, it's around going down from $2,400 to $640, a 73% reduction in cost. So if you look at today, this is 2012, this is 2022, and we're really close. We're actually making some progress. We're close in some areas. But as you know, in the beginning, you can have a great acceleration, but when you're coming to the target, you slow down a little. So we still have 6 more years to reach these goals over here, and we're really working hard on that. So the US government has a separate program called the Electric Drive Technologies Program, and under that program my group is working on different electric drive technologies to achieve these goals of power density, specific power, cost, and efficiency. So if you look at the vehicle, the blue boxes you see here are the boxes or the things we're working on. In a hybrid electric vehicle, you have a bidirectional converter that increases the battery voltage. Then we have the inverter, electric motor, battery charger with the plug-in electric vehicles. And this DC-DC converter is what powers your air conditioning system or your radio system. So these are individual targets per year. And for power electronics and electric motors, you see the cost numbers going down, the weight, power density, specific power, they're going down, efficiency going up. And when you look at these numbers, 2010 and 2015, they were actually met by, in this case, GM. The 2010 targets were met by GM, and 2015 targets were met by Delphi. 2020 targets are tough to meet. For the program, our goal is to come up with an electric traction drive system for 55 kilowatt peak power for 18 seconds, 30 kilowatt continuous power, and 15-year life. Talking to the car manufacturers, we understand that we cannot meet these 2020 goals. The cost target is really hard to meet. And if you think of the 30 kilowatt system, 55 kilowatt system, that was designed for a hybrid electric vehicle because you have a smaller electric system. So what we're looking at for electric vehicles is much higher power. So we're looking at higher power to increase this power from 30 to maybe 120, 130 kW. We haven't done it yet, but we're discussing with them right now, discussing with Department of Energy to increase this number. When we increase the power target to 120 kW, then we think we can meet all these targets. It's somewhat cheating, but at the end we say we met the targets. And there's no need to work on something that's not achievable. So this is a highlight of our research, a recent highlight for us. We worked with Delphi for a few years, and that Delphi inverter we worked with them on now is in the 2016 Chevy Volt. So any Chevy Volt you see, 2016 and beyond, until the third generation comes up, actually has our technology. So that's something very exciting to us. No, we're not getting rich, by the way. We're not getting any money out of this, but we're just happy that they're using our technology. So if you look at a typical hybrid electric vehicle power converter system, you will see the boost converter, like I mentioned, over here. And you usually have two inverters, one for the motor and one for the inverter. This is the one Toyota came up with, since they were the first ones anyway. And then this has been going on. This has been adopted by the others too. Typical voltages on the battery side, like 250, 300 volts. Toyota systems go up to 700 volt DC now, on the DC link. Car manufacturers, US car manufacturers, don't want to go to higher voltages. We tell them, let's go to higher voltages, reduce the current for the same power level, reduce the losses, have a smaller motor. No, they say we want to keep the same voltages and then still reduce the size of the motor and reduce the size of the power electronics. So that's a challenge. And we're talking to the battery people. They don't want to increase the voltages because it's challenging for them to put all those cells in series. So we'll have to live with what we can do with what we have over here with the voltages. Now let me show you some of these systems and what they look like. This is from a 2004 Prius. So we have a project where we buy these on-the-road technologies, the electric drive systems. We evaluate them in the lab, and then we take them apart, and then we see what technologies they are using. The reason for that is not reverse engineering. What we're doing is seeing what they're working on right now, because there's no need for us to do research on something that's already existing. So as a part of that project, we've been getting different technologies over the years, but this one is, I think, one of the first ones, 2004 Prius. So you see the shape of the power control unit is just random, nothing much. You see different parts of it, but when you look at the look inside, there's a separate inverter module and there's a separate boost converter module. This is the power module built for the boost converter. Then 2007 Camry. Their goal was, before 2007 Camry came out, was to have the power control unit the same size as your battery. The battery you would have in your car, the 12 volt battery, they said they want to make it the same size. So they succeeded with the 2007 Camry. Here you see the DC link capacitor, the inverter circuitry and IPM and boost converter. Now, this is a problem. The capacitor is too big and it costs a lot too. So in our research, we're not trying to find single solution. We're looking at parallel paths. Okay, and we have many problems we're trying to solve at the same time too. One of the problems we're looking at is reducing the size of this capacitor. How can we reduce the size of the capacitor? We can come up with new capacitor technologies. We can come up with new topologies, circuit topologies. So one of the things we worked on is a current source inverter, for example. What's one problem current source inverter has in an electric vehicle? Someone should know, right? You've seen current source inverters. Today they use voltage source inverters, not constant voltage. That's why we made the capacitor. Current source inverters. Okay. The main thing is braking. When you're braking, you're regenerating, right? How do you regenerate in a current source inverter? You can't, because you have a diode in series. It's going to block the current. If you cannot regenerate, what's the use of having an electric vehicle, right? That's one of the issues there. So one of my colleagues came up with an idea. Now, if you look at the voltage source inverter, you have the voltage constant, right? It's not changing. And the current goes in this direction or this direction. If it's going in the reverse direction, if it changes directions, then you're charging the battery. So he said, well, in a current source inverter, the current is always in the same direction. Let's change the polarity of the voltage. So he came up with a small circuit to do that. So that was one solution. Other solutions we have, instead of one inverter, traction inverter, we split the inverter into two smaller inverters, and they're connected to the DC link and they're phase shifted, now you have double the frequency on the DC link. So you can have your capacitor. Another solution, why not, there are 3 companies right now funded by the US government working on different high temperature, better capacitors too. Another thing I mentioned, the capacitors they use here are film capacitors. They are not electrolytic capacitors. Nobody uses electrolytic capacitors anymore for these applications. The reason for film capacitors is when they fail, they heal. They are self-healing. Ceramic capacitors would be much smaller, but the car manufacturers are worried that they would explode, and they don't want to do that. So when you look at the power module, here's a look of the power modules. 2004 Prius, 2007 Camry, and 2010 Prius. Now, one of the things I want to point out is, and it might be hard to see here, but here you see ribbon bonds. They are really thin wires connecting the chips to the external world. Here they came up with, these are wire bonds, these are ribbon bonds. Ribbon bonds are thicker. And in this case, they also added the boost converter H-bridge with the other inverter switches, so in one big block. Let's come to 2007 Lexus. They changed everything in 2008. This is a $105,000 vehicle, hybrid electric vehicle. If I had $105,000 to spend on a car, I would have bought a Tesla Roadster, the sporty one. But some people bought this apparently. So the difference in this case is, instead of using those big power modules with single side cooling, they used, I have another pointer and I'm pressing the button where we have the pointer, but anyway. So in this case they have packaged each IGBT and diode into single package and cooling it from both sides. Here, everything is cooled from the bottom, right? Here we have a system where you have the IGBTs and diodes all sandwiched between 2 metal plates over here. Okay, you can see the inside here. And that's how you cool, compared to this system where you have the wire bonds, like this. $105,000 vehicle was able to use that technology, newer technology. 2013 Camry, which is a $35,000 vehicle, it used the same technology now. Because over the years, from 2008 to 2013, they were able to reduce the size of their system, or the cost of their system. So we were excited about this one when 2016 Toyota Prius was announced a couple of months ago, and they're using the exact same double-side packaging. So I'm just going to show you the Nissan Leaf inverter. We're going to look, we're going to take it out and then look inside what's inside. So just to show you some of the sizes of these things, these are around 13, 14, 17 kilogram, and 16 liters, 11 liters, and 10 liters. So when you take the lid off, you see the big capacitor in this case, and some control circuits over here. You take the capacitor out, you see the gate control chips, and then you take that out, you see the 3 power modules. And each power module has all these chips, so they are using single-sided cooling too. Capacitor, when you see the capacitor like this, actually it's one block, but it consists of many capacitors over here. The bobbins here are these link capacitors, and there are some high-frequency capacitors also embedded in the whole capacitor box. Cooling. Thermal management is a big deal. So many times when we talk to the people, non-power electronics people, we say we have 97% efficiency. They say you're done. Why are you working on this? They don't realize that 3%, the loss, we have to take that heat out of the inverter, and that's not easy. So thermal management is really important. You can see the intricate designs they came up with in this case. Actually, if you look at the Toyota Prius one, it's more impressive, but they spent a lot of time just cooling, designing things to cool them. This was interesting, 2012 Nissan Leaf charger. The charger was the same size as the inverter. Inverter is an 80 kilowatt inverter. Charger is a 3.3 kW charger. This was just wrong. This was just bad. After that, they changed it. Now it's like a third or a fourth the size of the original charger. So I have this plot, the chart, just to show you the power levels we're talking about. 2004 Prius, 55 kW, Camry 105, Lexus 160, Prius, recent Prius 60, 30, 80. So these numbers are, mixed depending on how much of a hybrid you have. Now Chevy Volt has 120 kW electric drive system. So that's why we're looking at maybe 120, 130 kW as our target. We cannot pick exactly what Chevy Volt has because then Chrysler and Ford will not be happy with us. So we have to pick something in between. So let's build an inverter. Some of you might know what the components are, some of you might not, so I thought we can just go through. DBC, direct bonded copper. You have two copper pieces on top and bottom and ceramic in the middle. Then we put the chips on, solder them, put the ribbon bonds in this case, put the base metal, and we don't want that base metal, we don't like that. We're trying to see how we can eliminate that base metal because it just sits there, it's extra weight. And the way we design electronics today is, we get the power module, we get the heatsink, we get the capacitor, we get the bus bars. They're all separate because they're coming from different manufacturers. But we have to find a way to eliminate some of the components we don't need by integrating everything as much as possible. Then we have the encapsulate, the silicone gel. Some of you might like to play with it. It's very soft. It has three functions: mechanical, electrical, and thermal. Then, of course, you have the plastic package cover. So we built the module now. Let's build the inverter. So you have the heatsink, which is, when you buy commercial, it's usually a snaked heatsink. When you put the module here, thermal insulating material, 40% of your thermal drop is because of that. So that's another level, another layer we want to eliminate. In our projects right now, we're trying to eliminate that. We don't want to go with what's traditional, what's done traditionally. Then you add the gate drivers, add the current sensors, add the bus bars, controllers, capacitors, and you're done. So what are some problems we're facing? Now I'm going to show you some plots later, but whenever someone tells you their inverter is 97% efficient, what does that mean? It means it's efficient at one point. That's what they're telling you. And that's probably the best number they could get. Well, what about if you have an electric vehicle? Is your electric vehicle operating in the same areas where your motor is designed to be more efficient? Not always. So we have to know where your motor or inverter is operating at before you design it. You cannot just design for best performance. It has to be application specific. Devices, they have low current density right now, and we don't want to parallel too many of them, so that's an issue for some of the devices we have, especially the wide bandgap ones. For wide bandgap, we're looking for reliable, high temperature junction devices, because if you go to higher temperatures in these devices, then we need to cool them less, and then your cooling system will be smaller. The cost of wide bandgap devices, I'm going to show you some things on that. And we still have to worry about low voltage electronics and the volume they occupy. And they're simple, they don't cost as much, but they still occupy some volume. So just remember something. One of the interesting things working with the car manufacturers is that we are working on reducing the size of the inverter, okay? But there are these connectors. They are basically copper bars connectors. Everything is getting reduced. The copper bars, they are the same size. So now they're telling us, okay, we're reducing the inverters, converters, whatever, but how can we reduce the size of the connectors and the copper? I don't know yet, but that's something probably we'll have to work on later. So on the wide bandgap devices, any of you, are you familiar with wide bandgap devices? Silicon carbide, gallium nitride? Some? Okay. So they're supposed to have higher reliability, but the current devices are not really reliable. So everybody's asking if they're reliable or not. But these devices are just new. They're just recent. We don't have extensive testing of these things, long-time testing of these things. Okay, we'll find out. Eventually they should be reliable, but today they're not. If you ask Cree, they will say they are because they're using them in power supplies, but we haven't seen them in electric vehicles yet. They can increase the overall converter efficiency, higher frequency operation. That helps us reduce the size of the converter. When I say converter in our area is DC-DC converter. An inverter is not a converter, because I'm working with non-power electronics people and that's their definition. When I say converter, it means a DC-DC converter. Inverter or others are not included. Higher temperature capability. We've been working on silicon carbide devices since 2001, before many people knew what they were. Okay? And we did some packaging, and we even ran some of these things at 450 degrees C, compared to 125, 150 of silicon. Of course, if you ask me, I'm not going to tell you to run them at 450 degrees C, because you're losing efficiency there. And there are a lot of problems when you go to higher temperatures. With wide bandgap devices, you can get lighter weight, more compact system, higher power density. When I talk to the car manufacturers, there are three important things for them. The first one is cost. The second one is cost. And the third one is cost. Those are three important things. But recently, when I've been talking to them, they're talking about power density more. They will not tell me that power density is more important than cost, but I think it's almost the same to them right now. So that's one of the reasons they really like wide bandgap devices. So what we want to do is we want to get more miles from the battery, the same size battery. That's our goal. So I mentioned the efficiencies. Highest efficiency for this inverter is right here, somewhere here. And guess what? When you look at this motor inverter running on in a driving schedule, you'll see that it operates here a lot too. But the efficiencies there are pretty low, pretty lousy. So one of the advantages of wide bandgap devices is that their characteristics do not change with temperature or operating conditions much. So this way, we can maybe expand this area, get it wider. So it's not just the efficiency increase in one point where we can get 99% efficiency, let's say, with silicon carbide devices. We're also expanding the efficiency region so we can get higher efficiencies in these areas too. Maybe similar, really high efficiencies. Just a chart to show you what kind of devices are available right now. GaN FETs are usually for lower voltages. You have silicon carbide devices around this voltage level. And most of the higher voltage experimental devices are silicon carbide. Now, there are two kinds of gallium nitride devices. The ones you hear about today are lateral devices. So they are gallium nitride on silicon. Silicon carbide devices are vertical devices. So you can get higher voltage devices with silicon carbide devices and lower voltage devices today with the gallium nitride devices. But they are working on gallium nitride bulk material to build vertical devices too. But I went to a meeting a few weeks ago, and the presentations I saw that if you replace the word gallium nitride with silicon carbide, the presentations looked exactly like the presentations from 15 years ago. So there's at least a 15-year difference in technologies. And gallium nitride and silicon carbide, they actually work similarly. I don't know if there is a great advantage of using gallium nitride over silicon carbide. So we'll see what happens. But we still need to have 15 more years to actually come up with the right gallium nitride devices to be used where the silicon carbide devices are being used right now. So here are some of the devices we have seen which you can buy actually of silicon carbide MOSFETs, JFETs, and silicon IGBTs. If you look at the prices for the same voltage and current rating or similar ratings, the silicon carbide devices are in the 20s, 30s, 40s. Silicon IGBT is $4. If you look at the modules, you see a difference here to 5 times difference. This is the main reason people are not using silicon carbide in their inverters, converters for the vehicles. Let's look at GaN. GaN, you see they're at 600, 650 volts, not higher than that. And we think, even though some GaN people claim GaN can go to 3,000 volts, I mean lateral GaN, we think this is the voltage range it will stay at. And you see the prices over here. Honda, I went to a conference a few months ago, and Honda said they're going to use silicon carbide diodes in their inverters soon. 2-3 weeks ago, Toyota showed their all silicon carbide power control unit, which is 2/3 smaller than their current one. When I talked to them about when they're going to have these things in the vehicles, they said by 2020. So we still have a few years to go before these things are in the vehicles. So overall, we're looking at wide bandgap technology, integrate topologies, as I mentioned, to reduce the size of the electronics, control algorithms for better, more efficient operation, and better control of the devices too. These wide bandgap devices are really fast. You can run them really fast. Actually, the Cree people who originally were designing the MOSFETs, they said, don't even use a control resistor. Then what happens? You're running these things really fast. Like one of the professors today mentioned, the bearings, you have the EMI problems and the bearing currents increase. So you're impacting your motor in the same sense. And by the way, you're also impacting your inverter. If you're not careful with the EMI, it will impact your controls, your operations. But one of the most important things is packaging. You have these chips, and today when you buy silicon carbide devices, they are in silicon packages. They are not in silicon carbide packages. So their temperatures are limited to 150 or 175 degrees C, not higher than that. So some of the work we're doing in packaging, typically you would see the package like this. You have, like I showed earlier, single-sided. But now we're looking at how we can integrate everything into one package. So this is our package. This is a gold-colored package. Not gold, actually. But this is a double-sided package, just like the one I showed earlier from Lexus or Camry. Two things that are important in a package: the resistance and the parasitic inductance. So you want to run these things at high frequencies, right? Silicon carbide device, let's say. And if you have really high parasitic inductances, you'll have high switching ripple. And it's going to be really tough for you to control these switching. So for that, we're trying to reduce that. Reducing the online is parasitic resistance too, not to impact the efficiency. So the module we came up with, it has 2 IGBTs and 2 diodes. And it's the same size as one of these Lexus or Camry packages, but it has twice the IGBT and diode. So it says twice the power rating. So we're really excited about this one. So there are other ways of putting it together, with the integrate cooling. And we're trying to work on it more to see how we can integrate electronics with it and make it as small as possible, make the inverter or converter as small as possible. So if you look at different components in a vehicle, for the inverter, this is the converter, high frequency. Right now, they usually operate on 20 kilohertz on a vehicle. Even though we expect them to be 100 kilohertz or something, they're usually on 20 kilohertz. The inverter operates around 10, 15 kilohertz, not more than that. And so, that's more or less lower frequency. Then we have these DC-DC converters. They can at higher frequencies. The battery chargers, lower voltage, higher frequencies. So if you want to use silicon carbide or gallium nitride devices, there's a place for all of them. So for the charger, you can use gallium nitride or silicon. Or for this converter, again, the same way. We think that the inverter, for now, will use silicon carbide, especially if there's a boost and high voltage inverter is needed. So up to 600 volts, gallium nitride, lateral devices will be fine. 600 volts, 1200 volts, that's where silicon carbide devices come into the picture. If you go beyond 1200 volts, it's all silicon carbide. But those devices are not available. Today you can buy 1700 volt rated devices, silicon carbide devices, but they're still I don't think they have really high currents. We don't usually get those things and work on them. So both technologies can coexist in a vehicle. Now we're going to change gears a little. I'm going to talk about 3D printing. 3D printing is fast, less expensive, and better designed. What this means is if you're trying to, for some applications, let's say you come up with an idea and you want to see if it works. 3D printing really works really well. You just prototype it and then print it, and it's there. You can play with. You can increase complexity. You don't want to print a cube. A cube, you can just machine it and get it done. You can come up with some designs that you cannot machine, cannot be machined. Those you want to print. And for the same, let's say you decide to print a cube. If you have a really complex structure you want to print that uses the same amount of material as the cube, the cost is the same to you. So the complexity doesn't add anything, it's free. Less wasted material. When you machine something, machining is called subtractive manufacturing because you're taking things out, you're wasting all that material. 3D printing is called additive manufacturing because you're adding. I'm going to show you some photos about how that's done. So you're not wasting any material. So quick prototyping. And we're looking at how we can integrate functionalities, as I mentioned earlier, instead of having one capacitor, one module here and there. So this, as you can see here, small, simple drawing and titanium hand. That's a 3D printed titanium hand. The titanium printing is very interesting in the sense that you can adjust the porosity. Okay, so it doesn't have to be a block. So they printed some prosthetics for people. And there's some where they can adjust the porosity, so the bone, there was the prosthetics for a dog, and the bone grows into it. And it's much lighter than typically machined titanium piece. So these are some other pieces you can see just to show you, what can be done. This ball here, it has 8 more concentric balls inside, starting from small one to larger ones. You cannot machine that. Maybe someone can, I think you can. So there's a lot of videos on how this thing works. I'll just have a few slides for you to show you how this thing happens. So it's more or less like inkjet printing, but instead of liquid, you have metal, powder metal. You put a layer of powder, and then you melt certain areas. So you're melting the metal over there, and then you put another layer of powder. And by adding more powder and melting certain areas you want to melt, you start growing these different parts. So if you're interested in it, YouTube has if you look for ORNL manufacturing, you will see out of videos on that. So how do we apply this to power electronics? We can print copper bus bars. There's work going on printing PCBs. It's not there yet. Gate driver boards, of course, PCBs, heat sinks. We can print heat sinks. Power modules, there are parts we can print in the power module, but we're not going to print anything if it doesn't make sense. Now, one problem is multi-material printing. So it's really hard to print metal together with plastic because they melt at different temperatures, but there's a lot of work going on in that area too. I need to tell you, there's this, we're also looking at flexible PCBs. So I don't know if you remember transparencies for presentations from years ago. There's plastic, really thin plastic transparencies. So you can print regular print silver on the plastic. There are some inkjet printers, and then you can print like a liquid silver on them. Then you send these things through an oven. And then in a flash, you apply, I don't want to be lying, but it's like 500,000 degrees or something. So with that instant flash, the metal, the silver melts. The plastic doesn't. It's skin depth. So you can come up with different PCBs. So that's something also we're interested in looking at. But that's not really 3D print, additive manufacturing in the sense. So we 3D printed an inverter. When I say 3D print inverter, we didn't print everything, of course. This is 50%, we say roughly 50%. So here are the capacitors. Here's the heatsink. Heatsink you can see here from the top, from the side, and here are the X-ray images. This heatsink was printed in one piece. The only way you can machine it is in 2 pieces. You cannot machine it in one piece. And as you might have noticed, we have powder, right, when you're printing. That powder gets stuck inside if you're building something that's enclosed something. So in this case, the manufacturer was able to reduce all that powder. So then you can see these small structures inside, really high resolution structures you can print in these heatsinks. And then we have the package over here. Package has silicon carbide devices, our own DBC, our own package. And then the plastic parts are 3D printed plastic. And then we added the gate drivers over here. Did all the testing, got 99% efficiency. We didn't believe it. We took it out. We put a similar silicon inverter, got 97% efficiency. We tried that a few times. Usually when we tell people we have 99% efficiency, it's hard to defend it. But in this case, it works. The material, if you look at the material, here's the thermal conductivity of the bulk aluminum, regular aluminum. This is 3D printed aluminum. So when we first got this plot for different temperature values, we said, maybe we can come up with some alloys to add to the 3D printed aluminum to increase this at lower temperatures. Then talking to the materials people, we found out that actually, once we were testing this, going to higher temperatures over here, we sintered the 3D printed aluminum. So now if you come down, it's going to have the same characteristics as bulk aluminum. So 3D printed aluminum, same characteristics as regular aluminum. Then we said, okay, this inverter was very traditional. You put the capacitors, you put the heat sink, you put everything just one by one. Can we integrate some functionality? So we came up with this inverter we call the compact inverter, 80 kilowatt inverter. Here we have these other capacitors. The side walls are capacitors. You remember the big block, the big brick I showed you earlier? So these are much lighter, much smaller. Inside all the chips and the gate drivers, everything. Only the controller is out here. Then the top and bottom of these cylinders over here, there are 3 cylinders. The top and bottom are 3D printed aluminum. When you look at them, they look like just blocks, but inside there are cooling channels. So these top and bottom lids function as cooling systems. They also function as structural elements holding everything together. And they're also the plus minus DC bus. So we eliminate the DC bus over there because we're using it for this application. The top and bottom structural elements for that. And using wide bandgap devices, more intimate cooling of these devices, we were able to come up with this inverter that's almost half the size of the Nissan Leaf inverter in this case. There are other things to be done, okay? But this was a good progress, good step forward for us. Now we're trying to use 3D printing everywhere. In the US, the most important goal right now is manufacturing, and 3D printing is a part of manufacturing. So we're trying to do everything that makes sense in additive manufacturing. So in this case, here's another small module, small package we built using 3D printing. And when we built our converters and inverters, when we talk to the car manufacturers, they say, well, what's the volume of this? What's the size of this? It's really hard to say. So we started printing plastic shells around them. So when you close this, it looks like a regular commercial inverter. We also tried to print a 3D ferrite inductor E-core. It didn't work. It's almost like air. So there's still more work to be done there. Switching gears, going into motors a little. Someone mentioned earlier today about dependence on rare earth materials. So in the last, 50, 60 years, US has been working on electric vehicles to reduce dependence on foreign oil. So 5 years ago, they realized that using permanent magnet machines that use rare earth materials, they were trading that dependence with dependence on rare earth materials. So before 5 years ago, if I had talked about induction motors or switch reluctance motors, they wouldn't have listened to us. Okay? Now they're listening to us more. They're still using permanent magnet machines. But GM, first time in their vehicle, used the induction motor. They hate induction motors. So the main reason for that is this spike over here. Since China controls all the rare earth material production, they can, when they need money, they want more money, they can adjust the prices. So if you look here, this is around maybe $50 or so. When it peaked over here, $3,500 a pound. A kilogram, sorry. So now we're trying to eliminate the use of permanent magnets or permanent magnets with rare earths and design motors like that. The US has, these rare earth elements are not really rare. US has them too, a lot of them. But the problem is digging them is very dirty. They're out of radioactive materials. So the Environmental Protection Agency in the US will not allow that. China doesn't care. So we looked at different motors, different kinds of motors, some of our designs, some of the axial gap motors, those were really popular for a while. We came up with novel flux coupling machines, brushless field excitation machines, and we have an interesting switch reluctance machine too. You can find all publications on these. But some of the other things we're looking at in the motors is, for example, motor thermal management. We're still trying to cool the motors, but we're looking at where we can eliminate some of the cooling requirements. So one of the things is looking at the windings and how we can take the heat out of the windings. Okay, so we're looking at different materials, different coating materials, so different wires and everything. So here you see some of the coupons for different structures and different materials, looking into seeing which ones would be better for cooling the motors. Another one is looking at silicon steel. So if you use laminations right now with high silicon content, it will cost you 10, 20 times the regular lamination, regular steel. But if you use silicon steel, you can reduce losses by 40%. So that's another area of interest for us. We're trying to see if we can achieve that. Another project we have is we realized, talking to the motor designers and our own experience, when you design a motor, let's say you design a 100 kilowatt motor, you build it, you evaluate it, you get 70 or 80 kilowatt. The modeling is not accurate. One of the reasons for this is when you have the FEA software package, let's say you pick a certain material, certain steel. You don't know all the characteristics of the steel. All the characteristics are not really there. And you don't know how the steel is oriented when the laminations are stacked together. And you don't know how much manufacturing of those laminations, punchings, and laser cuts, they're affecting the magnetic properties of the material. So we're looking at all those things, trying to make sure that our modeling is more accurate. So for example, we developed this setup where we have these steel pieces, we're punching them or we're damaging them a little. In this case, we cut them into two and then splice them back together. And while we're doing this, you can see, by looking at the magnetic properties of these materials, you can see where the damage is. Okay, so the splice, for example, you can see it's right here. You can locate the splice because of the change in the magnetic properties. So this one is interesting here. We had a similar sample like this, and it had 5 laser pulses applied to it. When you look at it, you cannot see the difference. It looks just like regular, like it was before. But when you look at it through our setup, you see the 5 pulses where they were located. So this is another way of looking at how the manufacturing, laser cut, impacts us. Of course, we've also looked at how the punching in this case, impacts it too. So looking at the stress distribution, magnetic properties, looking at the magnetic domain analysis, this is not something, I'm still trying to understand all these two because we're working with computational people. They're basically building the material atom by atom from scratch. And then from that, they're trying to understand how steel grains and magnetic domains work. So I still don't know exactly how they're doing it, but that's another area of looking at how the material properties change. So all these things we're going to incorporate in our advanced FEA modeling tool, so we can reduce a 20-30% difference in accuracy. So here, for example, we have looked at some of the simulations, and you can look at the torque here and the power, the ideal case and the non-ideal case. You see the difference in that, and we're trying to make sure that the non-ideal case simulations we come up with actually are very similar to the actual evaluation of these motors. We also 3D printed a motor. The challenge for 3D printing a motor is, do we really want to 3D print these laminations and stack them together? That defeats the purpose. That's not very easy. I mean, already, getting these laminations chopped and then stacking them together, soldering them, whatever, putting them all together, it's a lot of work. So with 3D printing or at the manufacturing, we're trying to reduce the amount of steps. So we don't want to use lamination. We don't want to print them. So, why not print a block? Well, you cannot print a block of metal because of the eddy current losses. So we have to come up with something in between. In this case, we weren't worried about the efficiency. We weren't worried about the performance of this motor. We said, let's 3D print something and see how it works. So in this case, we had a block steel stator, rotor. We didn't print the wires. The wires we wound, and then we had the housing over here. We operate this induction motor. It's a very small induction motor. We just want to be the first ones up running a motor. I cannot tell you it's highly efficient or not, but this is something we want to be the first in. Now we have other work going on, for example, when we print these things, why not use, for example, soft magnetic materials? So you don't have to print laminations, you have blocks. But once you do that, you have to have filler material. When you have the filler material, if you have block metal like this, you have a certain size. If you have filler material, it's going to be bigger. So there's a challenge there too. But once we find funding, we're going to look into this more too. We're really interested in how we can get it more efficiently 3D printed. Switching gears again, wireless charging. I mentioned the charging work we're doing in the last 7 years. We have been working on wireless charging of these cars too. The main reason for this is mainly the convenience to the driver or the owner. But initially, the reason we came up with this idea was 7-8 years ago, the Department of Energy was looking into different ways of electrifying roadways. And one of the ideas they had was, let's say this is the car. They said, why don't you have an arm come out of the car? And on the side of the road, there would be a rail. And the arm would be really coupled with the rail. And then you would go at 50, 60 miles an hour. That didn't really make sense. So, to me, at least. So then we looked around and we found out that actually MIT was working on wireless power for cell phones. And the reason for that was this professor in physics department was getting in trouble with his wife all the time because his cell phone wouldn't work. Most of it would be discharged, so he wouldn't charge it often. So he decided to come up with wireless charging. So for us, we started 7 years ago with like really basic big coils, and then we retrofitted several cars over the years. We have 3 different scenarios we're looking at. Stationary charging, when you come home, you park your car in the garage, or if you're driving around, you put in a parking lot, you can charge your car. And by the way, there's a video, if you're interested, there's an animation on YouTube. If you search for ORNL, WPT, you can find it. Or if not, send me an email, and I'll send you the link. The second one is for buses or delivery vehicles because they have to stop in certain areas. Right? When they stop for a few minutes, they can get charged. The third one is in motion dynamic charging, where we can put all these either coils, that's our work, or rails, underground rails. And then you have certain charge in your car, you get enough charge through these coils to take you to the next set of coils without using any of the original battery charge. So that's another way of looking at it. This way, either you can have smaller batteries because range anxiety does not exist then if you're driving on the highways, or for the same battery size, you don't have to discharge your car while you're driving on the highway. And the Department of Energy was really interested in this one. We did a few cars, we retrofitted a few cars on this, and recently we finished this one. I'm going to tell you about that too. So this one, it was for stationary charging. These two we did for opportunity quasi-dynamic charging, and this little guy, we retrofitted for in motion or dynamic charging. There you see 6 coils. So we were looking at, if you drive this vehicle on the 6 coils, what kind of energies you can get. So one of the questions I get all the time is the health and safety. Okay, I call it the cat problem. Because most people say that when their car is being charged in their garage and their cat would crawl under the car in between the coils, what happens? Well, we will have to have some kind of presence detector. It would shut down the system. That's the quick answer. But we're not the health department. We don't do anything in health, but what we're doing is we have the standards for emissions, electromagnetic waves. So we're looking at measuring by the car, along the car, how far. To be on the safe side, we keep the people away from the car as much as possible. We have one person who's been driving this for 7 years. We let him. He's still alive, no problems. He's married, but he doesn't have kids, so I don't know if that will impact that one, but we'll find out over the years, I guess. So that's one issue. The other issue we hear from people is, what happens if you have concrete or pavement between the coils? Because if it's dynamic charging, it has to be under the pavement. So when we checked with the pavement, no problems, no losses, no additional losses. But with the concrete, there were additional losses because of the steel bars inside the concrete. That's why you have the losses. The other problem we're considering is McDonald's. People eat their burgers, take the wrappers out, they throw it outside, and then if these things go between the coils, we tested them, they get red hot. We stopped before the wrapper melted, but that's an issue too. Here's our latest setup. This is from end of March. So there's a Toyota RAV4 EV, all-electric vehicle, and here you see our coils. Now this coil is really close to the one on the ground, but this wouldn't be the way it would be in a car, but our project specified that we had to achieve certain power, certain efficiency through a certain gap. That's why it's kind of lower under the vehicle. So with this system, we got 95% efficiency from input to output. We designed the system. Our goal was 6.6 kW charging. But you know, we over-designed our boxes. Whenever I looked at the boxes, I said, only 6.6, these are too big. Well, we were able to go beyond 20 kW. Now we're confident that we can even go up to 45 kW with the same boxes and same coils we have. Those weren't optimized for 6.6 kW. But while we were working for DOE, this way we were able to test different frequencies, different switching frequencies. We like 22 kilohertz, but others have looked at, have been interested in 44, 85, 144. We have done all those things and looked at and compared the efficiencies and stuff, but we like 22 kilohertz. If you look at the standard is going after 85 kilohertz right now because Qualcomm is pushing for it. One problem with 85 kilohertz is the same frequency they use in your key fobs. So while you're charging your car, the car might be locked, unlocked, or whatever. So that's the challenge there. So numbers, if you look at the overall numbers, okay, air gap, we tried 160 millimeters. It should be 206 millimeters over here. From the wall to the battery, 85% efficiency. So do you know what the efficiency of wired chargers is? 100%? Almost? 92% or so, 92, 93%. Because wired chargers, you still have the converter. You have a rectifier, you have a DC-DC converter. Those are not 100% efficient, right? So with all those things, this is very close to wired charging. So we're really excited about it. So another question. This still has lower efficiency. Students ask me, which one charges faster, wired or wireless? Anyone? Yes? Who says yes? Wired? Why? Yeah. That's the trick. It's the same thing as which one is heavier, a kilogram of iron or a kilogram of cotton? They're the same weight, right? So if you design your wireless system to output the same power to the battery as the wired system, it will be the same. But your input power might be a little higher because of the lower efficiency, but what matters is the power or the energy going into the battery. And most people say wired. Most of the students say wired, by the way, when they come to our lab. All right, so we also did a dynamic testing. Of course, not high speed, just lower speeds. So here are 3 of our coils. This was very low speed because this was manual. First we did manually, see what kind of waveforms we're getting. And then we did with the car. So manually, we got this waveform over here. You see the 2 humps over here and over here when you're going over these 2 coils. I'm not claiming that this is the most optimum dynamic charging case because this wasn't the goal of ours. They just asked us to demonstrate it too. So there's a lot of work to be done here. But when we were actually doing the testing, we didn't get 2 double hump waveforms like this. Instead, we got one, and the second one had the double humps. And one double hump and single hump over here. Then investigating it although, we realized actually when the car was on both of the coils, since in our system we had both of the coils energized at the same time, there was some coupling from both of the coils. Even though the actual coil under the car is right here, let's say. Okay, it's aligned with this one. But this one still couples with things under the car. So there's still a lot of work to be done. Another question comes up. Does it really make sense? Can you get enough energy? I still don't believe this, by the way. I was involved in the calculations, but I need to see it to believe it. So if you go through all these equations over here, we get around 281 watt seconds, okay, or 0.08 watt hours when you're going over these coils. So with those numbers, 75% of the highway should be covered in coils. Our peak power in this case was 9.28 kW. We didn't do this at 20 kW. That dynamic one wasn't at 20 kW. So what if we can do 100 kilowatt instead of 9.2? If we did 100 kilowatt, then we get 7.5% of the roadway should be covered with the coils. We'll find out. There are other problems too with wireless charging. I mean, we're looking at ideal cases, but there will be so many cases where, you know, parking might not be really aligned, or, you know, kind of crooked, or these geniuses with all these things. So there are other things we have to look at, but this is a very interesting research area, and hopefully we're hoping to get more funding to work in this area. And this will also be a gateway to autonomous driving. I don't know if you heard what Elon Musk wants to do. Have you heard of autopilot? Tesla's autopilot, where it drives itself? What he wants to do is, if you're in New York, he wants you to order your car from California, and the car drives itself all the way to New York. The problem is, every 300 miles, it has to charge. The Tesla idea of charging is not wireless. They think of the snake, like the cord would come and then plug itself into the car, which kind of sounds silly to me, but that's what they're looking at. But if there was wireless charging, even at just in certain places to charge, it would make it easier. So we wrote a few projects on how we can use wireless charging to enable autonomous vehicles. 3D printing, going back to 3D printing again, this is not power electronics related in this case. So what can we do with 3D printing? Well, it's not for mass manufacturing yet. For certain things, for small quantities, you can do it. This is a great example. This titanium piece for planes. Apparently, they have to buy 11 tons of titanium to come up with 1 ton of this tool or piece or part. If you 3D print this, you don't lose 10 tons of titanium. You don't lose almost anything. So that's a great example of where it can be used today. For power electronics, not for power electronics, but for electric motors maybe at some point. If you come up with these rotor designs that cannot be machined another way, that could be used there, for example. How fast? It's not that fast. Those small pieces take around 3-4 hours to print. And it's very expensive. So how large of a prototype can we build? How about a car, a plane? A house. Good. So this is the world's first 3D printed car, working with a company called Local Motors. So this company, actually they moved their headquarters by our lab recently. What they want to do is they want to build cars locally. So if you're in Izmir, you buy your car from the Izmir store and they print it there for you. So that's why it's called Local Motors. And working with them, we printed this car over here. And another thing they want to do, let's say you get this car, you're driving it around, and you don't like it. You want it to look, I mean, or you have kids, you want the 4-seater. Then they can take the top off and print you one that would that will also have a seat for your kid or wife, whatever. So, or later you might want to have a sports car, you can take that out and put a sports car body on it. So that's what they want to do. So to print that, we have to have huge printers. We have a printer that's the size of the stage probably. It uses these carbon fiber infused ABS. Typical ABS 3D printed, it bows. But at the lab, some materials guys added carbon fiber pieces in it, so it's solid and very, very strong. And by the way, if you notice, this is a wing of a plane, cross section. So they're looking at planes too. This is a 3D printed Shelby Cobra. We printed last year, all electric. We didn't print everything, of course. We printed the body, printed the chassis using the same material. And was it, let me see, 2015, 2014 August, our management said, we want a 3D printed car by Christmas time frame, or by New Year's. So by the time, we thought they were joking at first, of course. We could print small ones, but not a fully functioning one. But by the time we realized they were serious, and by the time we decided what to print, from that day on until this car was finally in this form, it took 6 weeks. 6 weeks. The most of the time we spent was for acquiring components. We didn't build the motor or inverter. We didn't have time. We bought them from other places. So this car And by the way, the printing took 2 days. And we had to hurry up at the end because we had a special visitor coming. So we had to finish it quicker than they asked us to do, so that Obama and Vice President Biden can come and see the car. And he was asked to sign the car, but he declined. He said, other car manufacturers would be upset if he signed this car, so he didn't sign it. And Biden apparently wanted to drive it, but we didn't let him because we don't know how safe the car is. And some people think this is me, but it's not. I think I have a little more hair than him and darker.
Actually, he looks Donald Trump.
Well, Donald Trump has big hair too, so this. So for that, before the car was put together, we put everything in the lab. All different components were put in the lab after simulations, and even the accelerator. So you can press on the accelerator, you hear the motor moving, see the motor, all the currents, waveforms, whatever, you get those. And this is how it was printed, not in one piece, smaller pieces. Well, I mean, this small is this big still. The reason for it being us not printing the whole thing at once was because when you have a huge printer, print melting plastic with one head. So it starts from this point, it comes over here, and the original molten part is dry now. So when it goes back, it's really hard to do it. So we had to do it smaller pieces. So while this is still molten, it was easier to print on it. Of course, for the color, this had to be sanded and then painted. And you see the cooling here for the electronics. 2 fans in this case. Then they said, that's not enough. So starting in January, they said, we want you to 3D print another car and a building in 9 months. So this is a 3D printed building and a 3D printed car in this case. We call it AMI, Advanced Manufacturing plus Integrated Energy. And Jeeps are called printed as sports utility vehicles in the US. So this one we called printed utility vehicle. So the way it was printed in 2 pieces. If you think of C, let's say this, instead of an O, think of a C. Okay. That C was printed, the other C was printed, and they were bolted together to make one rib. And you put all those ribs together, you build the house. If you want to make it longer, you just add more ribs to it. This was designed by an architecture firm in Chicago. Apparently they are world renowned. And at the end, when we finalized this, it won several architecture awards. We engineers didn't like it as much, but other people liked it. The car was designed by engineers. That's why it's not very pretty. So when you look at the system, there's the battery right under the seats. There are 2 natural gas tanks. Actually, there was a natural gas powered generator put in the car. So the car, it's not an electric car, it's a hybrid electric vehicle, plug-in hybrid. So you can charge the battery, or you can use a natural gas engine to charge the battery. And also, we had solar panels on top of the building, and we also had wireless charging. So in this case, we had a 6.6 kW bidirectional wireless power transfer. First demonstration. So car powers the building and building charges the car. You can do both ways. The car can power the building from the battery or from the generator. Either way it will go. And the car, of course, can charge the building. So we had a big event, had hundreds of people come here. The Cobra, this has been traveling everywhere. It was really, it was never in the lab. It went all around the US. Then a few months ago it came to Europe. They shipped it to Europe, and in Europe it was in Paris for a while, then went some other places in France. Now it's in Hanover, I think. So we're always getting photos of this car with the dignitaries, like in German, whatever, Belgian, whatever. So all those people like to come and see this car. It's very popular now. This one is not very popular, maybe it's because it's not very good looking, but the building has been going around. The size of the building, the width was picked on purpose so it can be trailed anywhere. So it's been driving all around too, but the one question, okay, when you go in here, there's a there's a kitchen. There's a kitchen sink. There's a TV controlling everything. You see the dishwasher. There's a microwave. There's an oven and all these things. But you know, the kids, when they come in, the first question they ask is, where's the bathroom? There's no bathroom. It wasn't designed for someone to live. Okay, it's just certain things, yes, but certain things they weren't designed for someone to live. That's all I have.